So in this video we will solve the following problem. It says find the Maclaurin series of the integral from 0 to x t of cosine of square root of t dt and find the radius of convergence for this series. Then find g of a half correct to 4 decimal places. Okay, so we'll start with the function. Okay, g of x is equal to the definite integral from 0 to x t cosine of square root of t dt. Now, obviously, we will have to work. We will have to expand cosine of square root of t. So we have in mind cosine of t, the Maclaurin series is the sum as n goes from 0 to infinity, negative 1 to the power of n, t to the power of 2n over 2n factorial. And because this t and this t is the same, we can say, let's say here u. Okay, so just is going to be different u. Okay, now in our case, I have cosine of square root of t. Okay, so this whole thing here is basically my u here. Okay, so I have to use this formula, but instead of u, I will use square root of t. Okay, so this is equal to the definite integral, nothing else changes, t, the infinite sum when n goes from 0 to infinity of what? Negative 1 to the power of n square root of t to the power of 2n over 2n factorial dt. Okay. Now, I'm going to, before sending t inside of the sum, okay, I'm gonna simplify this a little bit. So this is equal to the definite integral from 0 to x t times negative 1 to the power of n t to the power of 1/2 to the power of 2n over 2n factorial dt. Now, from properties of exponents, we know that t to the power of a to the power of b is equal to t to the power of ab. And this, in our case, means that t to the power 1/2 to power 2n is t to the power 1/2 times 2n, in which these two cancel, and I'm left with t to the power of n. So this is equal to the definite integral from 0 to x t times negative 1 to power n t to the power of n over 2n factorial, and then this dt, this goes with the integral. Okay, now t here, this, consider this, treat it as an infinite polynomial, which it is. Now any polynomial multiplied by a factor of t, that means that this t will multiply every single term in this polynomial. Okay, so that means I'll have t times negative 1 to power n t to the power of n over 2n factorial dt. Now I'm here going very slowly, step by step, right? Of course, you can do this at once, right away. You can multiply t by t to the power of n, and you will get t to the power of n times t is t to the power of n plus 1 over 2n factorial dt. Okay, now again, I have to find the integral of this expression, but this expression is just a polynomial, so finding the integral of a polynomial is extremely easy. Okay, so this is the sum, negative 1 to the power of n. I'm integrating with respect to t, so I'm going to augment the exponent by 1, so plus 1, t of n, 1 plus 1 is n plus 2, so I divided by the same thing, n plus 2 divided by 2n factorial, and goes from 0. But now be careful, this is a definite integral, so I have to evaluate this from 0 to x. And I get the the infinite sum starting at 0, negative 1 to the power n, okay? T to the power of n plus 2, evaluated x, is x to the power of n plus 2, and then if you plug 0 for t, 0 to any power is 0, finite power, right? That is not 0, divided by n plus 2 times 2n factorial. And this is the Maclaurin series of this integral given here. Next, it asks us to find the radius of convergence of this series, okay? So we will use the ratio test, okay, in order to find the radius of convergence. I will use the limit of an plus 1 over an in absolute value as n goes to infinity. Okay, so an is equal to negative 1 to the power of n, this is my an, x to the power of n plus 2 over n plus 2 times 2n factorial. And then if I take the absolute value here, right, the absolute value would deal with this negative 1 or positive 1, or this negative 1 to power n. So I'm left with, look at the denominator is always positive, because n starts from 0, going towards positive infinity, n plus 2 times 2n, the whole thing factorial. But be careful, the absolute value I cannot erase the absolute value from x, right? X might be positive or negative, so that's why that absolute value has to stay there. Okay, so this ratio test can be rewritten now what is going to be the absolute value of an plus 1 in this case is going to be x to the power of n plus 3 over n plus 3 times 2n plus 2 factorial. Okay, so that's the limit of x to the power of n plus 3 over n plus 3 times 2n plus 2 factorial over an plus 1 over an is the same as an plus 1 times the reciprocal of an, which is n plus 2 times 2n factorial over x to the power of n plus 2 in absolute value. Okay, so this is the limit as n goes to infinity. Okay, let's see how we're going to write this down. X to the power of n times x cubed over x to the power of n times x squared. You really don't have to do like this step by step. I just want to write it more clear what's going to happen next. And then how do we cancel the factorials? Well, I'm going to express the bigger factorial in terms of the smaller one. So the smaller one is in the numerator, 2n factorial. And here I have 2n plus 2. So that's 2n plus 2 times 2n plus 1 times 2n factorial. And I'm going to stop here. Why? Because that's my idea, to cancel 2n factorial with 2n factorial in absolute value. Okay, so let's see what can we cancel now. 2n factorial and 2n factorial, x to the power of n and x to the power of n, and then 2 factors of x, leaving us with the limit of absolute value x n plus 2 over n plus 3 times 2n plus 2 times 2n plus 1 in absolute value as n goes to infinity. Now, the positive factors here are the factors involving n, right? So that means that only x will stay in absolute value. And then I have n plus 2 divided by n plus 3 times 2n plus 2 times 2n plus 1. Now, because this limit does not depend on x, I'm going to treat this absolute value of x as a constant, right? If you want, even if you can take it outside of the limit sign, if you prefer that. We're interested in what happens with the ratio of these factors. Okay, on top, I have a linear expression in terms of n. In the denominator, I have a cubic polynomial in terms of n. The limit clearly is going to go to 0. Of course, if you want to do it step by step, you can factor n from here, cancel with n in the numerator. The numerator in that case will go to 1 and the denominator will go to infinity. The idea is that this limit will tend to 0. 0 times any value of x is going to give me 0, and 0 is always less than 1. What does that mean? That means that for whatever x we put in here, or in other words, no matter where we evaluate g of x, whatever the value of x is, this Maclaurin series will converge because the ratio test is less than 1 independent of x. That's why the radius of convergence is infinity, is infinitely big. Or in other words, the interval of convergence is going to be from negative infinity to positive infinity. Why? Because, one more time, the ratio test gave us a limit of 0 independent of x, right? Which means that whatever x we take, this Maclaurin series will converge. And now the third question here, it says find g of 1/2. Okay, correct, accurate to 4 decimal places. Okay, so let's write down from the beginning what was g of x. We found that g of x is equal to the sum, when n goes from 0 to infinity, -1 to the power of n, x to the power of n plus 2, over n plus 2 times 2n factorial. Then g of 1/2 is going to be the sum, n goes from 0 to infinity, -1 to the power of n, 1/2 to the power of n plus 2 over n plus 2 times 2n factorial, or n goes from 0 to infinity, -1 to the power of n over, so the numerator here is 1, right, to any power 1, and then 2 to the power of n plus 2 goes in the denominator times 2n factorial. Now we have to find this sum accurate to 4 decimal places, so that means that we're going to stop adding terms once we see that the 4 decimal place is not affected. So let's list few terms here. When n is 0, the numerator is 1, so 1 over 2 to the power of 2 times 2, because 0 times 2 is 2, times 0 factorial, and 0 factorial is 1. Now n becomes 1, that makes this part here just negative, over 2 to the power of 3 times 2 factorial, plus 1 over, when n is 2, 2 to the power of 4 times 4 factorial, minus 1 over 2 to the power of 5 times 6 factorial. Obviously this is just augmenting by 1, and this is just the generator of even numbers, if that makes it easier for you to see these numbers. 2 to the power of 5, now it's 6, times this exponent and this factor are the same, so times 6, and then what was it, 0, 2, 4, 6, now 8 factorial, minus 1 over 2 to the power of 7 times 10 factorial, and this is extremely small number here. 10 factorial is a very big number, so 1 divided by 10 factorial is very small, So you can stop there. You will take the calculator in this case at this point and just start adding these terms, right? So this is going to be what is 1 over 8 minus 1 over 24 times 2, 48, plus 1 over 2 to the power of 4 times 4 times 4 factorial, minus 1 over 2 to the power of 5, 32 times 5 times 6 factorial, plus, and I'm going to stop here because I think this is going to be very small already, so I'm going to start calculating. 1 divided by 8 minus 1 divided by 48 plus 1 divided by 2 to the power of 4, 16 times 4 factorial is 24. So when I added these three terms, I got 0.1048177, and now I'm going to subtract this number here, 1 divided by 32 times 5 times 6 factorial. 6 factorial, this is a new calculator that I'm using, so I cannot find the factorial. Well then, 6 factorial, 4 factorial is 24, so 24 times 5 times 6. Now if I add, or in better said, subtract this number from this sum, the fourth decimal place will not change. The fourth decimal place will not change. So that means that I do not have to include any of the other terms from here on. That means that g of a half is approximately equal to 0.1048, or g of 1/2 is 0.1048 correct to 4 decimal places.